So welcome, everyone. I'm David Elbert of Johns Hopkins University, and thanks for coming to this year's Materials Research Data Alliance Annual Meeting, MaRDA 2025. Quick disclaimer, the meeting is being recorded, so by participating in the public discussion parts, you agree to having your participation recorded and posted on the web later. If you don't wish to do that, please only participate through the shared Google Docs, and the links through the Google Docs will be shared in the chat, as well as in the shared notes that logged in participants get access to. The fundamental goal in a MaRDA annual meeting is really getting discussion from the grassroots level going, so we have active participation in those shared Google Docs with one key to each session and breakout room. So to kick things off, I want to mention a couple of things. First, a quick introduction to MaRDA. We're a growing organization, so we're always excited to have new participants, and I want to really highlight then the essence of the MaRDA mission. It's simple. It's here on your screen. You've already read through it, I'm sure. We're really here to connect and integrate materials research data and infrastructure, and MaRDA does that by promoting this convergence of ideas, people, data, and tools. So we act as a national materials data network, if you will, as envisioned in the MGI strategic plan. We fit that MGI priority of building innovative infrastructure and the need to connect that infrastructure through this network. It's what we think really is in many ways the most important part of the puzzle, the human component. Materials data stakeholders have really diverse needs and goals, but they share values that support the need to connect and build a network of our networks. And that makes MaRDA a grassroots community, but led by organization for the human part of the infrastructure. So people working together to build connected, functional materials data landscape. I want to highlight here just a couple things about it. In a sense, we come right out of the MGI Strategic Plan 2.0. People are infrastructure 2 is the way I like to say it sometimes, this network. And on the right is just a somewhat fanciful view of what kinds of stakeholders we have in data, not just research PIs, not just data publishers, but computational facilities, experimentalists, professional societies, repositories, and so on. So we try to bring those together, and it's really one of the most exciting things about a MaRDA annual meeting is the fact that it's a place where all these different groups can come together and talk rather than just in their own special area. We have over 200 people registered for this week's meeting. But just as the focus on data and data-intensive methods is growing, MaRDA needs to continue to grow and build the network. And to help that growth, we're really excited to thank both NIST and the NSF for support of our programs and engagement. I want to specifically call out the council on the left, the elected MaRDA council, including Selena here in the I can highlight Selena in the middle, who's our communications specialist, who's done a lot of the real heavy lifting of trying to get us ready for a meeting here. But the entire council has really pitched in on a very short timescale this year to try to respond to a lot of new challenges and get us where we need to go. We meet every month. They're all volunteers, and so they really deserve a lot of our thanks to build things in the community. We also are excited about and grateful to the NSF for the Fair and Open Science Research Coordination Network program that has become a big part of MaRDA, shown on the right. And here we work on a number of different topics on fair data and fair models and workflows and making those impactful. And you'll hear more about those in a session specifically on working group outcomes tomorrow. So the general focus of the meeting, we've titled the meeting MGI Challenges from Data to Autonomy. There's been a lot of work over the last year and actually a couple of years on building out this idea of having grand challenges, MGI challenges. They are called right out in the strategic plan as something to accelerate the adoption and development, really, of the materials innovation infrastructure, the so-called MII. And a lot of work was done. Many people at this meeting were part of the MGI PI meeting last summer, where there were breakout groups specific to this, but there are a lot of other meetings as well. And so we want to introduce some of that and then talk about the state of these challenges. I think that some people in the community are still confused that we have MGI topics and we have more specific challenges. So we'll talk a little bit about that and a little bit more, provide some insight into how challenges can develop and the fact that we can develop new challenges and what makes a challenge. And so we've got breakouts this afternoon and tomorrow to work on that. But really then, let me turn things over to Benji and Cosima to give the bigger picture on the major activities of the last year that bring us up to this challenge moment. Dr. Benji Maruyama is a principal materials research engineer and autonomous materials lead for the Air Force Research Laboratory, Materials and Manufacturing Directorate. He pioneered ARES autonomous experimentation system for materials development with the aim of speeding the research process by orders of magnitude. Dr. Cosima Boswell-Koller recently joined the University of Alabama in the Office of Research and Economic Development as Executive Director of Research Engagement, supporting faculty and staff. And in that role, previously, she served as an NSF Program Director for the Materials Research Science and Engineering Centers, the MERSECs, as well as the Materials Innovation Platform, MIPS. Prior to that, she led advanced manufacturing materials and processing programs at NSEM, and she served as the science and technology team lead at the Naval Air Systems Command. Both Benji and Cosima have been directly involved in a lot of the activities that led up to the challenges, and so they're going to give us a bit of a background and work on that. So with no further ado, I'm going to stop my share and turn it over to Cosima and Benji.
Fantastic. And good afternoon, everyone. Thank you so much for the introduction, David. I will turn off my video because I'm working at a different setup and I'm not going to show the profile of my face, but pleasure to be here. Thank you for the introductions, and we'll get the screen share going here. So thank you again, David, and thank you for the introduction. We won't spend time on that, but we were asked to look at the strategic plan, the MGI strategic plan, to communities of practice, or our challenge-driven materials innovation, as a topic for today's meeting. So we wanted to give just a little bit of background on kind of how we got to where we are today. So if you're anything like me, I spend a lot of my spare time, whether that's a good thing or a bad thing, reading lots of reports. It seems to keep me current. But one of the things that we really saw in the last several years, and probably the last decade or so, if not longer than that, was this development of terms like AI, ML, and then moving into autonomous experimentation. So I just pulled a couple of the reports that I've spent the last several years spending lots of time with them to kind of benchmark this conversation. The first and most importantly for this meeting, of course, is the Materials Genome Initiative, or MGI. And we know from 2011, so about a decade, 14 years ago already now, that the Materials Genome Initiative really was looking at how do we discover, create, and develop new materials. And when we look at that traditional path of going step by step, it's very long, tiresome. It's kind of a linear path of trying to deploy those materials, and we often don't get there. With the MGI, we were looking at how do we really integrate an iterative feedback loop to be able to develop those materials at an accelerated pace by integrating both experimental tools, computational tools, as well as all aspects of data. So here we're looking at the update of the MGI strategic plan, or Strategic Plan 2.0, which was released in November 2021, which, my goodness, is already 3.5 years ago at this point. And here we're looking at accelerating that path by really having an iterative and multifaceted feedback loop and trying to accelerate more and more. And this here is the new integrative picture of that. And I think that was already captured on David's slide just a few minutes ago. So here we're really looking that there are no individual steps within the process, but we're constantly feeding information back and forth. So it's not one directional, it's multi-directional, it's iterative, and really having that co-design aspect. So why do we bring this up for today's topic? Well, if you take a really close look at the strategic plan from just a few years ago, Goal 1 states, one of the most exciting developments in AI approaches to materials R&D is the advent of autonomous materials research. And if you think back to my first slide, AI, ML, and autonomy is one of the consistent themes that we're seeing really burgeoning as a field. So within the Materials Genome Initiative, the 2.0, I took a look at kind of how often and where do we see these terms come up. And there's 13 mentions of autonomous in MGI 2.0, but then there's 40 plus mentions of AI and about 20 more of ML throughout that document. So it's obviously something that the community really has spent a lot of time and effort developing, as well as implementing to try to accelerate our materials design. To set the stage just a little bit more, this is a slide I developed about a year ago, and this is looking at every event that just I myself was involved with, starting about mid-2022 to mid-2024. So in about 2 years' time, these were all of the various workshops, various conferences, various meetings, anything involving autonomous experimentation or AI and ML-driven materials discovery. So there certainly has been a strong increase in activity in that space. And this slide, if it were updated, would be even more intense, even taking into account the last 6 or 8 months. So with that, I'm going to turn it over to Benji to define autonomous experimentation.
Thanks, Cosima. Great setup. Can you guys hear me okay?
Yes.
All right, good afternoon. Next slide, please, if you can just go build that. So really the context, right, is that we feel we're in the midst of a research revolution. And if we think about it in terms of, the Industrial Revolution, where machines took over labor, toil, if you will, and the compute revolution, which is a cognitive revolution, right? Computers took on cognitive tasks. And if you combine the two, you get the research revolution, where we combine artificial intelligence and AE, autonomous experimentation, to use robots to essentially do the manual and cognitive labor and speed progress by orders of magnitude. Next slide, please. And so we essentially started this area for materials with this Ares, our autonomous research robot, and talked about it in our 2021 community perspective paper. So that sort of abstracts this process, which really depends on iterative plan, experiment, analyze. Some communities call it design, build, test. There are other ways of thinking about it, but it's really doing something, seeing what happens, and then thinking and deciding what to do next. And so, the experiment has a lot to do with automation. So having a robot do that toil, that repetitive work for you, and then using things like machine learning or other kinds of artificial intelligence to see what happened and understand that in the context of what's gone before. And then the important part also is to act, right? To use AI and other autonomy sorts of algorithms to decide what to do next, and then go back and iterate and keep iterating until you're done. And so I think it's very exciting. It's been shown by numerous groups to be very effective and productive. There are speed ups of anywhere from 30x to 300x that have been quantified, but we think it can go even better. And it's not just, the machine learns something, but it can also be that we learn explicitly about different hypotheses, so explicit testing of scientific hypotheses. So that's the excitement there. Next slide, please. And so back in 2019, again, seems like a long time ago, we held this workshop, and I think some of the participants are here, but we really published that then in 2021 and gave a community perspective and really talks about things that we're talking about today. How do we get better decision methods? How do we think about better data standards, hardware, software interfaces, and especially workforce development? Next slide, please. And so go ahead. Yeah. So we then said, okay, let's now start to work on this as a nation, right? How do we think about what the US wants to do? And the context of this is that, for example, there have been significant investments outside of the US, $500 million by Canada. I've heard now about $1 billion in Germany. So what can the US government do to take all of the nascent efforts that are out there and try to coordinate them, especially towards US national interests? And so we came up with these points, this context there, and this is with Cosima, Lisa Friedersdorf, Jim Warren, Charles Yang, And that all built up to this all of government landscaping exercise that we did last summer in June. Next slide, please. And so it was a great workshop. We, from that workshop, generated an inventory of the National Autonomous Materials Innovation Infrastructure. So that's what do we have already going to set as a baseline upon which we can build, and also identify the gaps. So, what is it that we don't have that we need, especially at the national level, and then take those the infrastructure that we have, the gaps that we identified, and then use those to frame national and global challenges, which then led to the MGI challenges that we're talking about today. Yeah, go ahead to the next slide. It wasn't just the government who was doing that. It was great representation from the government, federal agencies, as you can see there, but also representation from industry, from academia, from national labs and NSF platforms. So tremendous participation, and it was a wonderful workshop. Next slide, please. So what were the findings? So we essentially built a report, and I say we, it was mainly Cosima, at warp speed, and presented it at the MGI PI meeting that next month, so from June to July. And here are the findings. There's the QR code to the report. I encourage you to not just go and look at it, but there's actually opportunities to contribute to it. So if you see something that's missing, please fill in the, so we can improve it. But, you can see the findings there, significant infrastructure, workforce development tools that I talked about previously. And then in these sunburst charts, here you can see that it's divided up by materials class. So structural, metals, ceramics, soft matter, and then functional in metal, ceramics, soft matter, and semiconductors. And so those sunburst charts really show what we have, and then by contrast to what we're missing. And really the assessment is it's early days, not really surprising, but that there have been key demonstrations of accelerated research and productivity. So this is essentially for real, right? It's not just a few of us talking about it, but some real solid demonstrations, and therefore worthwhile of further investment. Next slide, please. Okay. And as part of that, and then as almost a parallel path, Professor Donna Weinstein, who was at the White House Office of Science and Technology Policy at the time, ran a roundtable on autonomous experimentation for semiconductor materials innovation, and really using autonomous experimentation to shrink the timeline to solve this huge problem in sustainability in semiconductor processes, notably forever chemicals, PFAS being one of them. So you can see a number of us there, led by Donna. Next slide, please. And this is my last slide before I turn it back over to Cosima. That then resulted in the White House Office of Science and Technology Policy series of AI aspirations. So last summer, we were thinking a lot about what bad things might happen because of AI, and there was an executive order and restrictions about what could be done in the federal government. But the OSTP really wanted to think about the good things that could be done. And so out of that came 7 AI aspirations, one of which was materials, which is great. So there were very different ones on, education and roads and bridges, these kinds of things. But the one on materials came out of that roundtable, and so it was about semiconductor materials innovation for sustainable semiconductor materials. So very exciting. And I think there we turn it back over to Cosima.
Thank you, Benji. So really we wanted to set the stage, especially just give a little bit of background of kind of what the different activities have been and how these MGI challenges were created, and really looking at identifying how to develop really robust MGI challenges for the community to come together. Well, another thing that is called out in the Materials Genome Initiative is accelerating the adoption of the MII through national grand challenges. So the strategic plan, put forth that encouraging the MGI community to rally around addressing grand challenges or MGI challenges through targeted activities would be a potent means to accelerate adoption of the MII. So the MGI community should be brought together to define and develop solutions to national grand challenges through MGI-driven R&D. So Benji has already elaborated a little bit on this workshop that was held during my time at NSF. And it really was a great workshop, and it had a couple of different goals. So the first two really were identifying what capabilities do we already nationally have in the field of AI, ML, and autonomous materials innovation infrastructure. So that really is that conjunction of the AI and ML with robotics, but also then here italicized, identifying transformative opportunities and targets within the framing of national or global challenges. So how can we articulate very strong challenges that can be truly accelerated, but that we can also measure success by as a community, and ensuring that community voices are heard and that they contribute to this conversation. So during the workshop, we had 2 different days. It was a 2-day workshop. The first day was open to all of those invitees that Benji had shown the figure on, looking at academic participants, federal participants, industry, et cetera. So that was a very large workshop day of developing basically what came to be these sunburst charts, representative of potentially where our major emphases and major gaps are in autonomous materials innovation. The second day focused primarily on identifying those transformative opportunities, and it was an opportunity at the time for government personnel to discuss and develop ideas that really they saw missing within their portfolios that would be opportunities for the community to address and rally around. And this was developed into these MGI challenge, what I would consider themes that were then leveraged as a baseline for the MGI PI meeting, which was held on July 30th and 31st back at the Johns Hopkins Bloomberg Center in DC. And that is a meeting that is held every 2 years. Many of you have likely already participated in that one or the previous year's meetings, but really is an opportunity for this greater MGI community to be heard, to develop ideas and develop specifically for this MGI meeting, specific challenges aligned with these themes. So on day 1, the participants were asked to identify tangible targets for MGI challenges, and people self-selected into these 7 different themes and then had discussions. As you can tell from these speaker lists, they weren't just speakers, but really were leaders within those communities that were helping organize thoughts around the grand challenges. And the great thing about this, these sets of speakers, or we're noting them as speakers, was that there was always going to be at least a government employee, but also a participant from the community that is non-federal. So really, we were wanting to ensure at the time that this really isn't driven top-down and not just bottom-up, but it is a true conversation in developing what those targets and metrics could be and what specific challenges could be created. And then day 2, taking those MGI challenges was again looking at that benchmarking we had done in our June workshop to identify the opportunities and gaps in terms of the infrastructure needed to be able to accomplish and accelerate the accomplishment of those MGI challenges. The organizers of the MGI-PI meeting provided key elements that would make a successful challenge or MGI topic. It needed to have societal, national, or global needs to inspire a community to participate. So really something that many people are able to get behind. Scientific breakthroughs would be required, identifying the primary research needs that needed to be addressed. It needed to have a finite timeline, so something measurable, and a timeline, a suggested timeline, to be able to do check-ins to see if successful achievement or at least successful project is seen. And articulation of the requirements for that materials innovation infrastructure, again, tying it back to that physical as well as cyber infrastructure necessitated. The community, and I won't go into any details here because we do have a number of those leaders that participated at the MGI-PI meeting here to talk to us in the next panel session, but they were able to, at the end of the day two, be able to provide brief descriptions of what their developed MGI challenge was, the performance gaps that were going to be addressed, the objective of to be met, as well as key activities required to be able to baseline and achieve our goals. So just to kind of finalize here, one thing that came after this that I was very excited to see on January 17th, there was a notice of request for information, or an RFI, on autonomous experimentation platforms for the Material Genome Initiative. Again, this is, as Benji mentioned, that there's an opportunity to continue providing information and input on what this looks like nationally in the context of the MII. So this here is a QR code. So any information that you would like to contribute to this, to continue rounding out this set of information that we have nationally on what our capabilities are and where our biggest needs and gaps are, I think would be appreciated by the MGI subcommittee. I can't speak for them, but I think that's certainly something that they're going to really promote here. And also, developing the ideas around how do we then share infrastructure and leverage it to its fullest extent to be able to solve those grand challenges. Okay, Benji, to you.
Great, thanks. And so out of the workshop and with the MGI subcommittee, a set of grand challenges. So the MGI.
Oh no, folks, I think we may have lost Benji here. I think that's right. So I'll go ahead and we won't miss a beat here. So out of the work from the MGI-PI meeting, the MGI subcommittee was able to develop and publish 5 MGI challenges: point of care tissue mimetic materials for biomedical devices and implants, agile manufacturing of affordable multifunctional composites, quantum position navigation and timing on a chip, high performance, low carbon cementitious materials, and sustainable materials designed for semiconductor applications. Alongside, and there's a URL code, so if you haven't had a chance to look those, which I hope you all have, take a look at those at the link at the bottom of the screen there. But really also publishing a call to action, requiring innovative actions from not just the federal government, federal agencies, but also researchers, scientists, engineers, entrepreneurs, industry leaders, and all others along the entire technology development pathway. The community here is encouraged to join the conversation and bring those transformative approaches to leverage the resources and expand that materials innovation infrastructure to make the imagined future tomorrow's reality. So really, again, this ties into the slide we just presented with the QR code. We're still looking to enhance and identify what all of the capabilities are. There's constantly new capabilities emerging, and we need to be able to relay that information, articulate that information, share that information so that we can fully leverage the opportunities here. This is this here was Benji's slide, but I'll speak to it.
I can jump back.
Oh, he's back. There we go.
And hopefully I don't get kicked off again right at the wrong moment. But just on the last slide, I think you'll note that it was the 2024 challenges. And that was intentional, I think, on the part of the MGI subcommittee to say that, there can be future challenges. And I think there's a hope that there will be future challenges. So that was the first set of challenges. And I think there's certainly hope for future ones. If you go back to the next slide again, please. So what's been consistent through these workshops, the NSF workshops, the MGI workshops, and others, is that there is a need for coordination. So a public-private partnership for AI and autonomous experimentation, and for all of the reasons that we talk about, drive down risk and barrier, really have industry engagement with academia and government, cover all of the things that we need to in the U.S. national security, economic competitiveness, energy, environment, human health and welfare. But just to realize that there's a huge lift in building, modernizing our infrastructure, to think of it that way, to recapitalize our equipment base, which most of it is human only compatible, and how do we make it compatible with automation and autonomy. And then the last thing is to modernize our workforce, make sure that we can have a workforce that is prepared to do everything from basic research at university level to line operations in industry. So I think that's been identified as a pervasive need. Next slide, please. And I think that's the last one. Yeah, so just like to thank you for your attention, and looking forward to all the discussions that follow.
David, I think unless we have any urgent questions,
No, I think we should move right on to the panelists, please. So Cosima, can you fire that on?
Yeah, thank you. So I have the distinct pleasure to introduce our panelists for the session, the MGI Challenges panel. We have Tyrel McQueen. He is a professor in the Department of Chemistry, the Department of Physics and Astronomy, as well as Department of Material Science and Engineering. I'm never going to be able to remember all of those. At the Johns Hopkins University, he's also, I've worked with him closely, the co-director of Paradigm, one of the materials innovation platforms from the inaugural class, as well as a faculty member of the Institute for Quantum Matter, and expertise in new solid-state chemistry, materials design, and synthesis techniques. So we have Tyrel McQueen. I'll go ahead and do all of the introductions, and then we'll kick off. Tyrel, you can prep first. We'll have you go first. Then we also have Professor Donna Weinstein, as you saw already on the slides. She is a professor in Purdue's Elmore Family School of Electrical and Computer Engineering, and most recently was Principal Assistant Director and Special Advisor for CHIPS R&D and for Industrial Innovation at the White House Office of Science and Technology Policy, and was just so crucial in developing the AI aspiration for materials. So much appreciate her time here with us as well. We have Dr. Rich Vaia, who's a member of the Scientific and Professional Cadre of Senior Executives and is Chief Scientist for the Materials and Manufacturing Directorate at Air Force Research Laboratory, also one of our co-chairs on the MGI subcommittee for a number of years now. He serves as the Principal Scientific Authority and for Technical Contact for S&T, the S&T portfolio, for the U.S. Air Force, and his research has covered the chemistry, physics, and processing of nanomaterials for multifunctional structures, coatings, inks, flexible electronics, and optical devices. And finally, we also have Professor Katsuyo Thornton, who is the LNH and FNE Van Vleck Professor for the Department of Material Science and Engineering at the University of Michigan. Our research focuses on both computational and theoretical investigations of the evolution of microstructures and nanostructures during processing and operation. And we're very thankful for her participation here, as she was one of the co-leads for one of our breakout sessions at the MGI PI meeting. So thank you very much. I believe everyone has prepared at least a little bit of of information regarding especially the MGI-PI meeting, but also hopefully going to edge the community forward in what maybe there are some new opportunities to develop new grand challenges or new MGI challenges, and your thoughts on that. So with that, thank you very much, and I'll hand it over to Tyrel.
Okay, so a lot of this, a lot of the first couple slides here, I think were covered very nicely by Cosima and others already, but just as a reminder, you know, of course, materials underlie our world, but the materials research has been growing exponentially. But one of the most interesting things from a sort of actually making materials perspective is that a lot of that growth has been driven by predictions, not by actual realization of materials in the world. And that's, of course, an important thing, because in order for materials to be useful in any of these grand challenges, we have to actually make them and have them exist in the world, right? And, you know, and AI has just sort of accelerated this this disparity, you know, where, you know, you can in short order make hundreds of thousands of predictions of new materials, whether you know their properties or not, but actually then realizing them, you know, in real life, which is what then makes them useful, has become a real bottleneck, right? So there's this widening gap between sort of predictions and realizations. And, you know, this is, I think, one of the reasons why there's all this interest in both autonomy and automation from a sort of a doing things perspective, because, you know, if predictions are coming much faster than the ability to make things in the lab or in for real life, you need to figure out how to make more things more quickly. And so in the case of, you know, not so much the purview of MGI per se, but in molecular systems, right, there's the last decade has sort of seen this rise of what this particular article calls cloud labs, but it's basically, you know, sort of general purpose synthesis tools that you can drive entirely remotely, right? And this idea has been pitched in the context of a broader sets of materials and what's called materials acceleration platforms by people at Fraunhofer in Germany, among others. And, you know, previously these national reports were already mentioned. And what it really does come down to is the infrastructure, the infrastructure, the infrastructure. You have to have the infrastructure to be able to do these things, right? And without that, you know, you can think of challenges all day long, and still not make any headway. So as was mentioned, you know, in July, there was this MGI-PI's meeting, and I thought it would be useful just to reprise the community of a couple of the ideas that came out of that meeting that sort of help set the stage for possible sort of grand challenges that can bring the community together. And so one of the parts I was helping with there was information communication technology. So these are going to both be ICT related. But the first one was what I'll call a near-term sort of objective, which is to deal with the fact that electronics in our world consume more and more power. And at some point, power consumption, you know, exceeds what we can possibly make. And so we've got to find a way to address that. Right. And so, you know, data centers use about 3% of electricity right now, but this is expected to grow to 10% by 2030 and even further beyond that. Right. And at the end of the day, you know, you can't just address this by making more and more power. You have to actually improve the amount of useful computation you get per amount of power extended. And so, you know, this led our group at this MGI-PI's meeting to identify specific targets, you know, basically reducing losses by a factor of 10 in semiconductor devices, reducing volumes, and then cutting the sort of the highline numbers, so the overall facility usage data center power by, you know, factors of 2 or more. And in order to do this, there's actually a lot of materials challenges that have to be addressed. So, you know, and this basically comes down to when you make things small, how do you make things small and keep on-off ratios in transistors really, really high, right? How do you address the fact that when you make things really small, you tend to get low breakdown voltages, right? When you do generate heat, how do you efficiently extract that heat so that it doesn't have a detrimental effect? And almost all of these things are limited by the quality of the material and the quality of the growth of that material. And in particular, going beyond just stoichiometry or composition to really the actual full three-dimensional arrangement of atoms, some sort of idea of crystalline perfections. So that was one grand challenge area. So the other grand challenge area that was sort of identified by our group that's a bit further looking into the future was the dreaming up the, well, what might you think? And so, of course, tricorders from Star Trek come to mind. And can you make sort of a version of that that uses all of the potential of quantum technologies to actually do some novel things? And so this is based on the observation that quantum sensors, whether you want to think of atomic clocks as a kind of quantum sensor, or more scientific examples like gravitational wave detectors, right, are already enabling scientific breakthroughs. And quantum computing itself is in what I might call the vacuum tube era of computing, which is to say it's like normal computing back in the vacuum tube era, which is you can do some things, but it's not really, we haven't really hit the transistor and the things that you can scale a lot yet, but that will happen. And the question is, what materials needs are required to make those things happen? And so you can again go through the same exercise and identify that you need to improve existing sensors or new sensors, and reduce the physical size of hardware to that of a smartphone. And one of the interesting grand materials challenges that this brings up is not just how do you scalably manufacture these things, but how do you actually cool them, right? And how do you maintain coherence? And these are sort of grand challenges that no one understands. So these are a couple examples of areas that were identified as importance. And I think I'll leave my comments, just in the interest of time, with this point of actually making stuff, and the potential of autonomy and automation to actually help make stuff is a great interest of mine, and I think is important to the community. And so in December of 2024, I helped run a forum on the future of synthesis. And you can go and check out many of the talks from this forum at the website that's given there. But what we learned from this was we heard a lot from participants about how they've tried to deploy automation. And the central challenge, and maybe this is the idea I want to leave you all with, the central challenge seems to be automation and autonomy are really good at doing the same or very similar things again and again and again and again until you optimize something. What they don't seem to work as well for is doing a variety of new things. And so I think that's the real actual challenge in getting to true autonomy to accelerate discovery for materials, is how do you encapsulate, how do you make those systems able to do as wide a range of different things as can be done by human workers? And so I think maybe I'll leave it there.
Thank you very much, Tyrel. So we'll go ahead and I think leave questions to the end and then for the panel. So Donna, if you wouldn't mind going next. Thank you.
Sure. All right, wonderful. So thanks again to Cosima and Eric and everyone else for setting up this meeting and for the invitation to participate, and for setting up kind of an introduction to what I'm going to discuss, which is on the opportunity for materials innovation and acceleration, specifically for semiconductors. So as Ben mentioned, I had the privilege of serving in the Office of Science and Technology Policy over the past year as a sabbatical, and got to really work across the government to help lead microelectronics R&D, and all of the investments, all of the coordination for infrastructure, workforce development, for innovation and emerging technology opportunities, and the full spectrum. And through Lisa Friedersdorf and the much of the MGI team here was introduced to the fantastic work going on in materials innovation through autonomous experimentation. And this just sparked such an important bridge to our challenges in the semiconductor industry. So as many of you may be aware, we are at this inflection point in AI, which is why many of us are here right now. But that is not only driven by, but demanding of the semiconductor industry bigger, better, faster chips and more of them. And for the US, that also means kind of creating our own capacity building of the leading edge technology, as well as more legacy node capabilities. Microelectronics and chips in general are necessary across a wide gamut of applications. And we've seen disruptions to the supply chain affecting various sectors. But moving forward, we need to build that capacity in the US. The CHIPS and Science Act helped to incentivize some of that growth. And now, alongside the huge demand from generative AI and AI capabilities writ large, there's all of this move and push forward to manufacturing of semiconductors. So the industry needs to keep pushing forward on performance, which they have and keep innovating on in marvelous ways, and put much of the resources and efforts into that space. And so power, performance, area, cost, and time to market are key benchmarks, PPACT, are key benchmarks for the industry. Manufacturing capacity more recently has also been a strong demand, especially given supply chain resilience and growing databases for AI. And so with that, the announcement and the construction of many new fabs is coming up. In order to meet that demand, we are breaking the earth because semiconductor manufacturing and computation within these data centers takes up so many critical natural resources. So environmental impacts are huge. Everything from greenhouse gases and PFAS to water and electricity usage. And that goes, of course, to data centers as well as other sustainability issues, thinking about where we're sourcing our materials and if they're coming from mines employing, slave labor. All of those different parameters that the semiconductor industry has to think about when they're innovating in materials and in device architectures and then in chiplet ecosystems, it's an intangible problem. And so thinking about accelerating that materials innovation, building in important qualifying and qualifications and certifications of materials early on in the discovery process, so that we're not spending years after, after the first steps of innovation in a new material to actually get them deployed into high volume production. That can now start to be considered in the first stages of materials design and in the design of experiment, leveraging autonomous experimentation. So Benji, again, spent some time talking about this, and I think it's an exciting and important opportunity that we all need to jump on, semiconductors and otherwise across the research community in materials. I'm excited to, start deploying autonomous experimentation in my lab and at my university, and then, thinking about what we're doing nationally and globally to really, really push the envelope on innovating in materials. There's a lot that is needed to make autonomous experimentation successful and accessible to the broader community. And the NSF MGI report that Cosima and Benji spoke about earlier enumerates many of those challenges, some of which are listed here. And we really, really need to work across all of this. Data and the Data Alliance really bridges all of these different aspects, because we need to be thinking about not only the physics-based models and how to refine them, the physical infrastructure to provide data to refine those models and to really make valid directions for the AE models to be performed, or for the AE synthesis. Safety and security play a overarching role, and of course, education and training. All of that also requires a national consortium, which I think is very important to the database. What that national consortium looks like, I think maybe hopefully in the next few days, we start to refine what that looks like. There are very successful pieces, clusters already coming together. How do we create public-private partnerships that are incentivized in order to do that, including our international partners? But thinking more about the data and the models, I think this is where a lot of us, when we're thinking about implementing materials innovation, materials acceleration in new areas, are really, this is kind of the seed and the most important success factor is understanding our kind of starting parameters. And right now, I think there are very big gaps, especially when it comes to more complicated multi-film, multi-material, complex geometry devices and systems, where our physics-based models don't really translate well to understanding, what synthesis parameters will translate to the right material properties that we're looking for. There are efforts, I think, across the MGI community, across autonomous experimentation, to look at refining those models, creating AI, AE-driven improvements in that space. And I won't list everyone who's working in that space because I'll inevitably forget someone. And but actually, I think Cosima's report has a good outline of starting points in that domain. But translating, perhaps performing retrosynthesis and thinking forward-looking on reduced order models that encompass more complex physical phenomena, molecular dynamics, for example, replacing more traditional DFT, now enhanced by AI and shared federated data across the community, could enable things like ferroelectric materials, which could be optimized not only for memory, but also for sensors, for directed energy and optical coatings in that domain. There are so many different applications of the same material system, and understanding how that those synthesis parameters translate to material properties is a really, really crucial part there. We need to, as we do that, think about reliability, yield, and cost. Thinking about when I go to etch these materials and define particular nanoscale and micron scale geometries, stress relaxation and interfaces that are going to completely modify the performance and the behavior of maybe not my material, but the device, contact resistance, and all of these different factors, and thinking about designing from material to system and the co-optimization necessary to go there. So we need to bring in the co-design EDA, that's kind of the electronic automation, automated design folks, and think about bridging across the multi-physics domain to optimize at the system level for any new material. So there's a lot of exciting opportunities there. I think we need to work together across the different fields, speaking different languages. And then the big question of how do we build up the data given, what exists, but protecting IP, protecting the interests of the industry and the competitiveness of the industry, while kind of opening up the space for new materials and new design. So I'll leave it there, and happy to discuss more.
Thank you so much. We'll go ahead and Katsuyo, if you wouldn't mind sharing next. Thank you.
Okay, so thank you very much for the opportunity to present today. I'm presenting on behalf of the breakout 4 and 5 of the MJ meeting that was mentioned. And this represented the thoughts from all the discussion leaders who are listed over here and the 50th breakout participants. So the breakout 4 was titled Enhancing Structure Performance. The breakout 5 was titled Protecting the Environment. So those two topics are quite distinct, and so rather than the specific of each of the breakouts, I'd like to focus on the common threads between the two breakouts, and then I believe those are the common threads in other breakouts as well. Okay, so the just to quickly cover the challenge topics that came out of the two breakouts. The several challenges topics came out for breakout 4. We had two topics, one corresponding to primary metric structure materials, where MJ approaches were adopted, but there was still a gap in translating into deployment. The challenge topics, there was a model-based quantification of structural materials. And another topic from this same breakout was the 3D predictable, manufacturable, low-cost polymer composites for transportation. And so they're still like developing phase in terms of MG approaches, developing science and tools, etc. The breakout 5, the first topic is the materials for the built environment. Cement, such as cement and cement replacements, development of environment protected polymers, high level chemical separations, including water separations, CO2 capture, chemical removal, etc., and heterogeneous catalysis. And I think these topics that came out of the breakout 5 are kind of similar to the polymer challenge, where science and tools are still being, quite a bit being developed. So common gaps, here are the common gaps that are pointed out in both of the breakout reports. In terms of material performance, there's still property gaps. That is, if we can make materials with enhanced properties, we can significantly improve the performance of these materials. So we need to somehow be able to make new materials that have enhanced properties in order to achieve that goal. The examples of that was the strength, toughness, stability under high temperature stress or other type of conditions, as well as lightweight, which is essential for the efficiency, energy efficiency. In terms of gaps in tool, the predictive models along with uncertainty quantification is lacking, especially when the tails of the distribution are critical. The experimental tool-wise, there are tools lacking, especially when it comes to chemical characterization in complex environments or on-field evaluation of components. Finally, both breakouts identify the challenges in collecting and using data, especially those applicable to service environment or under component, that has a consistent geometry or loading conditions, etc. Some common themes from the two breakouts, as well as their objectives: difficulty translating research and development to deployment. But emerging materials are not making full impact quickly. So this is a big challenge. I think today there's still this value of death type challenge. I think part of this challenge is the qualification of the material for specific applications. It's very time consuming and expensive, and that delays the deployment. So the qualification is challenging, and we also need to enhance reliability sustainability and manufacturability to close this gap. So that's this point. And we also need additional fundamental understanding, uncertainty quantification, both the science and of it and the tools, predictive models, and ways to conduct rapid testing and integration of all these concepts and tools. And as you know, we heard already, AI and AE both play a major role in that. Okay, so the here are some common key activities. So the AI plays a role in all of these activities, but development of framework that integrates various components, broad access to experimental capability, and largely lacking is the life cycle assessment of materials that needs to guide the material development. And then I think this is really important, the successful demonstration with quantified benefits to foster cultural changes to address the new materials, modeling, and sharing data, and to the need for engagement with the industry in order to get their buy-in. And then another way to work to do this is to work with the younger generation, educate and train future generation of engineers and the scientists who are ready to, embrace modeling approaches, integration, and data sharing, etc. So we already, Cosima already presented these 5 MGA challenges, and 2 of them came out of the breakout. And just a parting thought, I really want to emphasize the successful demonstration, this is the point, successful demonstration with quantified benefits to foster cultural changes, to embrace new materials, modeling, and sharing of data. What I noticed is that sometimes we get to the kind of value of that kind of thing, and then we kind of stop, and then we go to new materials and look at fundamentals, right? And I think we really needs to be balanced in terms of the topics and activities that are beginning to embrace MG approaches, and those further along in that development, and pave a way to faster translation and application of technologies, developing techniques for qualification and the translation to technologies and manufacturing. So that's my thought, and thank you very much for your attention.
Thank you so much, Katsuyo. And last, certainly not least, we have Rich. Thank you.
I appreciate the opportunity. I just want to add a couple, I guess, synthesizing comments. Great brief out of everything that happened at the MJI meeting last summer, and hopefully gives the community an idea of the breadth of the input, discussions, and synthesis that came along. What I'd like to do is, before we jump into Q&A, is just kind of take all that and sort of synthesize it one level up about, what does it mean to the community? I think the first slide, I'm from the Air Force, so I'm going to use an Air Force example, but there's many examples. I think we all understand that the use of materials underlies technology revolutions. There's the picture of the Wright Flyer. I think we're all familiar with the story, but we may not be familiar with the role of materials in that story. The first is how materials were the enabler. Charlie Parker, who was their machinist, came up with a materials processing technology, a thin wall casting for the aluminum crankcase of the engine. At the time, he didn't realize it, but what he formed because of the cooling and the thin wall cracking was Goodyear-Preston zones in the aluminum alloy, which super strengthened it, allowed him to lightweight it, and allowed the power plant of the Wright Flyer to actually meet requirements so it could fly. So it was truly aerospace lightweighting through materials and processing. A few years later, the flip side happened, which was the first casualty of powered flight at Fort Myer, just on the other side of Arlington Cemetery, where a propeller snapped in flight, causing the Wright Flyer to crash. It snapped mostly, or some regards, because of inadequate manufacturing controls and materials metrology. The propeller was overseasoned, it was too brittle, it didn't match the design, they didn't have good material properties to understand the design constraints, and it broke. in flight. And so it's an enabler and as well as a limiter, but in all sense, it is because of the data knowledge, the materials knowledge that was necessary if you think of it in today's technologies. And that's really what we're here about, is that the MGI, all these challenges, all these great examples is really about how as a community, we can invent the stuff that makes the future faster. And these are important. Inventing is doing something new. The stuff is the materials that everything underlies. Making it is it's not just having the material, but how do you do something with it? And of course, the future. And we need to do it faster. And so using that thread, I'll just bring out a couple things that I think we've talked about so far that synthesizes this all together. First is the use of materials. We acknowledge it's different and it depends, its uniqueness depends on its use. So when we talk about the materials innovating infrastructure, it's not about a single bullet. It's not about a single entity. It's not about a single investment. The work that Cosima talked about and Benji, huge investment already existing. The question is, how do we build networks on top of it? How do we build the right network for the right use of the right material so we can accelerate? That's a big question. We'll find gaps in the process by doing that, but exercising that will allow us to move faster. But if we also not just use of materials, but using materials, we have to understand who is the customer for the materials. And that is the development engineers. And that is understanding what form the deliverable needs to be in. A block of goo, a single crystal is not what a development engineer needs to create a technology. And so delivering trusted data and verified and validated models for their decisions in design, pushing forward a materials maturation level of some point is really key to this. It's also understanding the ilities, the sustainability, the manufacturability, the affordability. How does all of our data knowledge lead into those types of things? And then access to stuff. We have to make sure we have those tools so people can decide when they need to do mid-scale scale up so they can do stuff. And so understanding that we're just not generating data for discovery, but we're generating data so people can make decisions further along the development and design and implementation pipeline is key. And taking that into consideration back in the discovery phase through an innovative infrastructure that's data-based has huge implications and cost savings that everybody from folks in industry through government to academia or through industry is I think motivated for this. And then at the end of the day, it is accelerating it. We're not saying anything new here. What we're talking about is how do we do it faster? And that really boils down to adopting digital concepts, so digital workflows and digital knowledge. We all know how to do discovery. We all know how to do deployment. How do we do it faster? How do we use workflows to understand where those critical points are, and then use the tools of AI and ML to solve those impedance mismatches? So it's not about accelerating or automating or using autonomy to do it all. It's about stepping back and using it intelligently to accelerate the overall process. So when we talk experimentation, I think many people think about in the lab making things. But really, I think experimentation is about testing the questions and hypotheses. And that's about integration of what we do physically, what we do in models, prior knowledge, as well as theory. So when we talk about experimentation, it's bringing it all together. It's not just doing something in the lab, but how do we integrate all of this stuff throughout that entire life cycle, from discovery to development, design, deployment, and decommission. And doing it and thinking about this as early as possible in the process just makes it more valuable to everybody along the process. So hopefully that's provided a little bit of synthesis of all the specific ideas and information presented prior, and really where these grand challenges, the themes, the topics fit in. We need, as a community, to really continue to demonstrate value and impact of the MGI approach all across the ecosystem of materials. And it's important to do that collectively with the ability to share successes because we have to sustain the investment of that ecosystem of the materials innovation infrastructure. And that's only going to be sustained and continually created as we continue to generate examples of value from metals, from semiconductors, from ceramics, from soft matter across the entire ecosystem. So really excited that MaRDA has allowed the MGI subcommittee to kind of bring some of the thoughts and the work that's been done. And a huge thanks on behalf of everybody for their engagement over the last 24 months. Cosima's slide that summarizes things is just jaw-dropping. It's all grassroots, driven by the community with huge excitement of potential. So looking forward to continuing to drive this and use this dialogue, this framework of the topics, the challenges, to be able to synthesize the community to not only do discovery, but bring in that whole entire all the parts of the enterprise that's necessary to not just accelerate one part of the process, but accelerate everything through the pipeline.
Thank you so much, Rich. And that concludes the presentation portion of the panel. So I think we can stop. Perfect. So thank you all very much for reiterating kind of what has occurred and some of your additional thoughts here. I do also have the privilege of introducing someone that I don't think really requires an introduction. If you don't know Dr. Jim Warren already, you certainly should. Jim received his PhD in physics at UC Santa Barbara and came to NIST, I think it said 1992, as a postdoc, and has spent an amazing career there. He's the director of the Materials Genome Program at NIST, and he has been involved with the MGI since its inception. So everything that I've told you about, that everyone else has been told you about today, he has been there since day one. So really excited to have him also join us here for the panel discussion, as well as David. And we want to make sure that we answer any questions that you have. And I believe, David, you have already started collecting a few of the questions through our note feature. But then I'll kick it over to Jim if you have any questions to kick us up.
And I just, before Jim jumps in, I want to say that we're running late. Shocker. So the poster session that was supposed to start at 2:20 Eastern time, we're going to move that back by 10 minutes. So we have time for discussion here, and we'll extend it by 10 minutes at the far end. So we have all these folks here. We're going to take advantage of having some discussion. So please go ahead, Jim, if you have things that you want to kick off, and then I'm going to look at the Google Doc for questions to bring.
Great. Yeah. So, I mean, I don't have a lot. Except to say, you know, it was really great to see that actually quite compact summary of sort of where things now stand, and a lot of the thinking that has gone into that has really bubbled up from the community, particularly in the last year or so, around these topics. And then as we start to discuss the challenges as a way to really focus the energy of the community on some very specific problems, and I guess we'll talk about this in more detail as we proceed. You know, and you'll look at these problems and you'll be like, well, I don't know about that one. But of course, underneath each one of these are a tremendous number of very interesting technical, scientific questions, in addition to some of the engineering challenges. And sort of depending on what what really gets you excited, we really do believe that there's a place for just about everybody in the broader materials R&D community in these spaces. So that would be my sort of high-level comment. I know, Dave, you've been thinking a lot about the questions, and the community's itching and to ask them, and we're very short on time, even with the extension, so I don't want to eat up any more time.
Yeah, well, and panelists may also ask things that have been raised from listening to others as well. But I'll start with a question from Ken Kronline. Was there discussion in the plan around these challenges about high throughput experimentation and identification of rapid proxy measurements in addition to automation of traditional experiments?
So maybe I happen to do a little read ahead here of the questions, and I did take the MGI strategic plan and just did a very cursory find all. And yes, it certainly does come up. And I do think that from my recollection of these various multiple years of, attending these workshops, having conversations, I think high throughput experimentation is certainly has come up quite substantially in discussions. And generally where I think it comes up a lot is really as that rapid proxy measurement, right? Whether we can do cursory high throughput at a lower quality to be able to get those first indicative directions in which we then can go down to a more or less granular experiment to be able to refine and really identify. But that's where I've seen it come up a lot in these conversations, but I'd love to hear the thoughts of the panel on specifically how you've heard high throughput experimentation. And I think that can actually be extended, not just the physical experimentation, but theoretical simulation as well, right? Being able to do coarse grain first and then be able to look at directions.
That's another opportunity for the pitch on the RFI, which very strongly looks at the intersection between the challenges and autonomy. And so it's living in that space. So obviously there's a lot of recognition of that. Of course, the very ideas you were just talking about, Cosima, around starting granular and then refining is exactly how a lot of these algorithms work in autonomy, right? So it's even baked in some sense to the way that they function. Go ahead, Donna.
Yeah, sorry, I was trying to figure out how to electronically raise my hand, but there are too many React
Figured out the
features.
analog way. That's good.
So I think in addition to all of that, some of the questions that come up for us on semiconductor manufacturing, the equipment is so expensive. You have to think about making devices, pseudo devices, not just the materials themselves. And so thinking about how to parse out, and this is where some of the AI agent and those models can be helpful. Parallelizing different aspects of the experiments to run concurrently, thinking about leveraging multiple facilities and doing short loops of some aspect in one and some aspect of the other. And that then, that's dependent on the material model itself and what can be separated and what cannot. So that's another important thing to consider that is very material and device specific.
Go ahead,
We'll
Tyrel.
go with Katsuyo first.
Oh.
She's unmuted right now, and then we'll go to Tyrel.
Okay. Yeah, I definitely agree with what's been said. But in the discussion with breakout 4, one of the main topic was polymer composites. And there was still lack of predictive models there, which makes it difficult to actually combine, close the loop. And also the lack of experimental capability for rapid manufacture testing, inspection, etc. Those are also lacking as well. And there was a significantly emphasis on more broad access to these capabilities.
Am I unmuted? Yeah, I am this time. Okay, good. So I think all the previous comments are actually good comments. A couple other places I've seen this show up. So I mentioned this forum on the future of synthesis at MRS, and there was a very interesting couple of messages related to high throughput experimentation and rapid proxy measurements there. So the first was that obviously having rapid proxy measurements is a prerequisite for doing many things faster. So on the one hand, you need it. But on the other hand, we heard from a couple of individuals at that event who pointed out that actually the reason so many materials don't actually get to deployment is that they don't get hung up, is that the rapid proxy measurements don't actually capture the most important properties that matter for actual deployment. So one can't just blindly say, well, let's do rapid proxy measurements and this solves all our problems. It's not really that in fact, it's a more complicated problem than that. So that's, I think, maybe the additional thing I heard that was interesting and related to this.
David?
Yeah, I was just going to jump in as someone who actually runs a data center that supports 2 high throughput projects that come from the Army, one Birdshot based out of Texas A&M and one HT Max based here at Hopkins, that in both those cases, high throughput is in the name of the program, and it's supposed to really not only be high throughput, but smart throughput. And as Tyrel said, that often means doing various things at a proxy level to figure out how you get to the next level or to screen things. but especially when we go to robotic manipulation and things that are fairly expensive to put the pieces together on, really figuring out what instrument is going to be on that line that will serve a number of different projects means there are a lot of practical aspects of what you do before you then figure out which samples you need to take out and put in a TEM or something that doesn't have an automated high throughput thing yet. And those automated steps are all obviously precursors to autonomy. It's nice to talk about autonomy, but you need automation and decision making to get yourself there eventually.
Any final thoughts?
Not, I'll drop another question that comes out of the Google Doc from Prabhakar, which says that in the aerospace materials field, one of the limiting aspects is scarcity of data for training AI ML models. From an industry perspective, tools that reliably address data scarcity for accelerated materials development and deployment would be really valuable. So pointing to this need to make data a product of our research as a primary product, which I'm sure several of you would love to comment on.
And I did see Rich unmute.
Yeah, I mean, I'll just comment. I think, I mean, I'm not going to disrupt industry's business models. But you know, to some degree, I think there's a question of when sharing data at a pre-competitive level helps an entire community rise, rather than the cost of reproducing the data within a company for just qualifying the same thing over and over and over again in each of the individual companies. And so that also, by the control of that data, limits the broader innovation community from using that data to discover the next thing. So definitely there's tools to address scarcity of data in developing models, but I think there's also opportunities through the MGI to establish partnerships with industry where the demonstration of sharing data can lead to value that they may not have envisioned, potentially new market opportunities where that data is shared at a pre-competitive level. I know a lot of the semiconductor community is driving in that direction, where new devices are built on a community of data and a community of techniques, not a vertical within each of the companies. So data is incredibly important, and being able to share it appropriately, but still maintain the ability to develop unique products from is a big, maybe not technical question, but I think a business question that, if solved, can lead to a lot of very rapid developments in science and technology.
Thank you. I saw Jim's hand next.
Yeah, just to add on that, you know, the whole idea behind the MGI in some sense is about lowering barriers to access for technologies. And of course, lower, you know, so if we're talking about autonomy, you know, we're talking about not just how do we do it, which is hard, we know that, but also it's, you know, how do we make it easier for more people to be able to do it, right? So it's the whole infrastructure idea, right? That's undergirding that. And so the easier it is and the cheaper it is, right? The more data you can essentially generate as a byproduct of the autonomous process, in addition to creating material, which you're after, you're also gaining knowledge, which then feeds the models, which is a virtuous cycle. So I think that, you know, the sort of the rows that we're plowing right now go right to that data shortage, right? Which we've been talking about since the beginning of the MGI. You know, and arguably all the conversations have been about, we don't have any data. And also a lot of it initially was about, well, how do we do compute better? How do we predict? Because data is, you know, so expensive. Now it's interesting to watch this conversation turn again to experiment as we're starting to open those doors. Over.
Great. If there are no other thoughts on that, let's squeeze in one more question, which is I actually had a question about how challenges reach across stakeholder groups. I mean, essentially the last question spoke to some of that, right? The data can transition from low TRL to high TRL and should. But I think also this idea of, as we're designing challenges and thinking of new challenges, we have an ongoing or long-term issue in the MGI of getting a lot of people at the research level involved, and it's a lot harder to get designers and people at higher TRL and in the manufacturing space involved. Do we involve them at the beginning in the challenge so we build collaborations and meaningful things? Do we think of some stakeholders as responding to a challenge, like, oh, this is what they're doing, so I'm going to make a repository? How do you all see us building those relationships from the start, or trying to do it later, since it is its own big challenge for us?
I think I mentioned that a little bit. Oh, I'm sorry. A little bit in my presentation, but you know, I think we need a successful demonstration of the entire process. And sometimes, you know, the funding is more available on the front, like the beginning part of it, and then kind of, you know, the tapers down, and then just the little push to go, you know, go across the, you know, the finish line sometimes is lacking. And because maybe scientifically it's not as exciting when something, you know, is already demonstrated in the lab. And you know, I think translation to manufacturing can be, you know, less, the funding for that is less available, and maybe that can be changed.
Donna?
Yeah.
From our perspective, some of the biggest challenges involve translation from kind of that first prototype of a material or device to high volume production. And so in terms of leveraging AE and the tool sets that are going to be representative of what is going to really be synthesized and even characterized at high volume production, it is, at least on the microelectronics side, I think really helpful to get the industry involved very early on. The Charisma program out of Department of Commerce that was launched kind of alongside, or as a alongside all of the CHIPS R&D investments and aligned with this autonomous experimentation, it really speaks to that. But creating the opportunity for AE exploration in the academic and low TRL levels, but having industry bought in and committed to benchmarking, to including what's relevant to them early on in the process. It lowers the barrier and lowers the risk for industry to get involved in this, but they do have to be bought in from the beginning and an important player throughout the research process, so that they can keep informing what's going to be relevant to them at the end of the day. So I think it is important to get them involved and engaged early on. Whether that is capital investments, I think depends on the industry. Some of the industry is already looking at those investments within their companies, and this is a great opportunity to upskill their workforce to be able to actually implement AE within their high volume production facilities.
Yeah, I'll just add, I think you said two really important terms: relevant and risk. And that is why industry needs to be involved. At the end of the day, each step along the way costs exponentially more dollars in the next step. Having them feed back what really is going to drive the trust, because the decisions on the engineers to use something is about trust. If I'm going to ask them to use a new metal in an airplane, I better guarantee it's going to work. Because when I go on an airplane as a consumer, I don't want it falling out of the sky. And so there is a huge amount of understanding the socioeconomic aspects that industry brings along that is so critical in prioritization and communication, and what is that data you have to discover and develop, and then how you feed that into their models that develop design and trust. And we always have to understand it's more and more money each step along the way. And again, I'll just add that I think autonomy is really great. But at the end of the day, it's about trusted data and trusted data for their ability to make decisions. Autonomy is one way of doing it. Using AI and ML is another way to do it. Human innovation and intuition is another way to do it with our workforce. Really, the exciting opportunity, I think, is how all this comes together to accelerate. One doesn't trump the other. It only trumps it when it solves the problem better and faster. And so I think high throughput experimentation, autonomy, using an AI, ML in the right places to make better decisions, discover new issues scientifically. It's all these tools used in the right place at the right time. We have to figure out the limits of all the tools, absolutely. But when we talk about using them to accelerate something, we'll use the best ones that are possible that we know to accelerate, not necessarily choose a winner a priori. And industry thinks that way. Over.
I'll just add one thing really quickly, just that industry also involves everyone from, the chemical suppliers all the way to the end users. And so we need to think across that entire value chain.
And I did see Tyrel unmute, so maybe we can give Tyrel the last 30 seconds.
Yeah.
No, okay, he's
No.
ditto. Done.
No, I mean, no, I mean, I think all the keywords were already mentioned for this one, right? I mean, I think, and earlier the better, because it doesn't matter how good it is if it can't be integrated or it can't be made uniformly and quickly, right? So the sooner you involve people, the better. Or if it fails after 10 years,
Excellent.
And
Katsuyo?
just 10 seconds. Yeah, I totally agree with everything that's been said. But one of the topics that came out of the breakout 4 was the qualification. Focus on qualification, and I think that's very essential in terms of accelerating the deployment of materials into new technologies.
Agreed.
Fantastic. So I think we have to call it there, because even though we gave ourselves 10 extra minutes, we're even 5 minutes over that at this point. But I really very much appreciate this robust discussion. I hope we can continue this actually using those notes documents. So any additional questions, we can monitor those, and then hopefully be able to actually develop some thoughts from there. So with that, David, I will turn it over to you for next steps.
Thank you. And thanks to all the panelists. The presentations were great. And that was a short but great discussion and gets us going. So thank you so much. So for next steps, actually, I'm going to turn it over to Selena in just a second, but I want to share the agenda just to say that we finished that panel. So we're going to go into our poster session now, and we've budgeted an hour. We're going to take a full hour. So I think Selena will get us kicked off into posters here at 2:40. And then we'll come back at 3:40, and I'll give you a little introduction. Next will be breakouts, and it's on these same topics that panelists just spoke to, and there'll be shared docs for each of those, and a chance then we'll have enough time to come back in and shorten closing remarks today and report outs to try to really flesh those out, and I'll give you some more ideas of that.